It's molecular interpretation of pressure and temperature of a gas, and it is consistent with all the gas laws and Avogadro's hypothesis. Mean free path is the average distance between two successive collisions. That is, it is the distance between two successive collisions. Pressure of a gas at STP is directly proportional to 1 by V, or it is inversely proportional to the volume of the gas. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to start a new chapter here today that is known as Kinetic Theory of Gases. So we are going to study what Kinetic Theory of Gases is all about. That is the way gas actually moves, or simply the dynamics of gaseous particles. So let's get right onto it. So what exactly is kinetic theory? What exactly is it dealing with? That is, when we were studying gases, the way we conducted the studies were confining the gases to a particular space so that we can observe them, and we varied various parameters of that particular container. That is, we varied the amount of volume that can be present inside this container using a piston wall. Then we varied the amount of pressure using the same piston arrangement, and we introduced various amount of temperature into the system. Like that, we controlled various parameters and we studied the behaviors and characteristics of these particular gases. So then we plotted certain graphs and we came up with certain laws, and that is what you're going to study in this particular chapter. So kinetic theory of gases mainly deals with what happens to gases under certain conditions, or simply how gases actually move and why that particular movement or dynamics came into effect. And remember that most of these theories are still slightly outdated, but again we have to start from the very basic and learn to the up-to-date condition. That is, most of these laws are only applicable to ideal gases, which you have already learned in your chemistry syllabus. But again, real gases will slightly vary from this particular behavior, but that you will study later. So let's first see why kinetic theory is necessary for us, and then we'll see what kinetic theory holds for us. So why exactly is kinetic theory relevant? So it is relevant because it does not break certain laws and it is consistent with those particular gas laws and certain hypotheses, and it correctly explains certain characteristics and natural behavior of these particular gases. That is why we still have kinetic theory and why we are studying kinetic theory of gases. So we can say that the kinetic theory of gases gives molecular interpretation of pressure and temperature of a gas, and it is consistent with all the gas laws and Avogadro's hypothesis. So what exactly are the gas laws and Avogadro's hypothesis? We'll discuss very soon. And it correctly explains the specific heat capacities of gases. Why gases seems to have that particular specific heat capacity. That is also explained by kinetic theory of gases. And it relates to the measurable properties of gases, like why certain gases are more viscous or why it is more diffusible. That is the process of diffusion. These characteristics or this nature of the gases are much better explained using kinetic theory of gases. That is why this law is actually relevant for our NEET. Now, again, when we are discussing about kinetic theory of gases, you have to imagine that in a broad container, we are filling it with lots of gas molecules. So the gas molecules are allowed to move freely inside this particular container while we vary certain parameters, and then we measure and observe what happens to the gas molecules inside the container. Again, even if the system is moving, we don't care. We are only bothered about the molecules that is inside the particular container. That is the observable thing we are focused on. So let's see what are the things we need to understand the kinetic behavior of gases. So the first thing we have to understand is that when these gas molecules are trapped inside a huge container, these gas molecules inherently possess some energy due to its internal energy. So again, these gas molecules with this internal energy will be in random motion. That is, some molecules will be going to the left, other molecules will be going to the right, X, Y, Z, in every direction possible with all sorts of velocities. So when this is happening, a few molecules are bound to cross each other's paths and they will collide with each other. So we know that this is bound to happen. That is, the molecules are bound to hit with each other and with the walls of the container. So that is why we formulated two different terms, that is mean free path and relaxation time. So what exactly is mean free path? Mean free path is the average distance between two successive collisions. That is, it is the distance between two successive collisions. When a molecule is colliding with another molecule and it is again colliding with another molecule, what is the distance between those two collisions? That is known as mean free path. And you don't have to study the derivation or how this particular law came into effect. You just have to know this particular equation that gives the length or simply the mean free path of two collisions. So L is equal to 1 by root of 2 pi n d square, where n is the number density of the gas and d is the diameter of the gas molecule. And similarly, the time between two successive collisions, that is, the length between two successive collisions, is known as mean free path. Just like that, the time interval between two successive collisions, that is, the gas molecule hits one, rests for some time and hits the other. So this particular time delay or this particular time interval, it is known as relaxation time, generally indicated by the Greek letter tau. So relaxation time is the time interval between or time between two successive collisions. So that is all about mean free path and relaxation time. Now it is time to start with the gas laws, or simply the ideal gas equation, the ingredients for the ideal gas equation, which is summarized by these particular gas laws. So you have already seen them in chemistry, but still we are going to refresh your memories. So Robert Boyle was a scientist who again was studying the behavior patterns of gaseous matter, and he discovered a particular relation. That is, again, the experimental conditions for all these gas laws are very similar. So you have a gas molecule or gaseous matter inside a container with a movable piston, so that we can adjust the pressure, volume, and using the heat supplied, we can also control the temperature inside that particular container. So in this particular container, Robert Boyle observed that the pressure of the gas and the volume of the gas were actually related. So again, these are not new inventions these physicists are making. These are just basic observations that are being noted down. So again, if you increase the pressure, that is, if you push down this particular lever, then the molecules will become cramped together. The molecules will have less space to move around, which means they will hit each other even more, contributing to the pressure inside that particular container. So in that particular case, pressure is increasing, but in this particular case, volume is also decreasing. So we can say that as volume is decreasing, pressure of the gas is actually increasing. So Robert Boyle observed that pressure of a gas and volume of a gas is actually interrelated, and he formulated the theory that pressure of a gas is directly proportional to 1 by volume, or simply pressure of a gas at STP is inversely proportional to its volume. So, and one more condition, this happens at constant temperature. At constant temperature, pressure of a gas at STP is directly proportional to 1 by V, or it is inversely proportional to the volume of the gas. Now this is known as Boyle's law. So we can say that P is directly proportional to 1 by V, or simply PV is equal to a constant, or one more way of writing it is P1 V1 is equal to P2 V2. So you can have many types of equation for Boyle's law. The only condition is that temperature should remain constant, or simply the temperature should not change for Boyle's law to be applicable. And if we draw a pressure versus volume graph, for this particular condition, then the nature of the graph we obtain is a curve like this. So we will obtain a curve like this. So as pressure increases, volume decreases, or as volume increases, pressure actually decreases. So this is the relation between P and V observed by Boyle, or simply Robert Boyle, known as Boyle's law. But there is one catch to be noted, that this particular condition or this particular behavior is observed for gases only at higher temperature and lower pressure. That is, at higher temperature and lower pressure, yes, these gases are perfectly behaving like what Boyle expected. But there was a catch. When he performed the experiment, not at STP but other different temperatures and pressure conditions, then what happened was that at higher pressure and lower temperatures, the gases actually deviated from the ideal nature. The ideal prediction was broken by the gases. So real gases seems to be deviating from the ideal behavior. So instead of having this curve, the real gases were having different curves like this. So it was observed and understood that for a gas to behave perfectly theoretically, that is how we predicted, for that gas to behave just like that, there should be a specific temperature and pressure region. So we say that at high temperature and lower pressure, gases behave ideally, which means that it will follow this Boyle's law. and all the coming laws, that is the Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's hypothesis, everything will be followed by the gases ideally, just like in the theory, if it is high temperature and lower pressure. But if the pressure conditions and temperature conditions are varied, or it is in the real life situations and it is not at STP, then we can see that these gases will deviate away from the ideal gas behavior. Yes, they can be having a predictable pattern, but it will be deviating away from the ideal gas behavior. This deviation is because real gases do not obey these ideal gas equations at certain temperatures and pressure. They only obey these laws and conditions at high temperature and lower pressure. That is something you should never forget. So again, Boyle's law is PV is equal to a constant at constant temperature. Moving on, the same experimental setup. Now the only difference is that instead of keeping the temperature constant, I am going to keep the pressure constant. Now I am going to keep the pressure constant. Now what will exactly happen? So that was actually observed by another scientist known as Charles. So Alexander Charles first observed this phenomena and he noted it down. So it became as Charles' law. So Charles' law states that, so it was Alexander Charles who actually observed this particular phenomena and he noted it down. So what he observed was that keeping the pressure constant, if you increase the temperature of a system, the volume of that particular system also increased. Again, if you take this simple experimental setup, you can understand it very clearly. So there are gas molecules like this trapped inside this particular small container with a movable piston wall. So if I supply heat, or simply if I increase the temperature inside that particular system, then automatically the molecules will start to vibrate even more faster, absorbing all that particular energy. So when the molecules are vibrating faster or it is hitting everywhere, it also hits the top of this particular piston walls. So what happens? The piston actually races upwards. The piston races. So again, when the piston races, the volume evidently increases. So we can say that as temperature increases, the volume of a system also increases. And this happens at constant pressure. So we can say that at constant pressure, temperature of a gas is directly proportional to its volume, or simply V by T is equal to a constant. So this is known as Alexander Charles's law, or simply Charles' law, and this happens at constant pressure. So again, if we plot a graph between volume and temperature, you can also take it temperature versus volume, both are same. But again, if we plot a graph between volume and temperature, keeping the pressure constant, then the nature of the graph we get will be a line like this. That is, V is directly proportional to T. So it will be a straight line with a positive slope, just like this one. And they can also ask you a numerical question, that is, if this is P1 and this is P2, that is two different graphs drawn at two particular pressure regions. So which one of these will be having the higher pressure? That is a common question that can be asked. So how can you generally predict which one will be having a higher pressure? So we can just simply say that from the ideal gas equation, PV is equal to nRT, or just simply PV by T is equal to nR. And let's say that only one mole of gas is being used, so I'm going to use N as 1. And I'm going to take the P to the other side, so I can say that V by T is equal to R by P. Again, R is a constant, so simply I can say that V by T is directly proportional to 1 by P. So V by T is directly proportional to 1 by T. That is V by T again we know that V by T is equal to a constant value, which means that this will be a constant. So if this graph increases, the pressure should automatically decrease. If this value decreases, the pressure should automatically increase, which means that P1 here will be greater than P2. So P1 will be greater than V2. So that is According to the slopes, you can identify which pressure will be more, which pressure will be less. Again, similarly, we can also say that this also, that is Charles' law, is also only observed at higher temperatures and lower pressures. If the pressure is different, if the temperature is different, then automatically it deviates from the ideal gas behavior. Instead of having a straight line like this, the gas actually deviates from the ideal gas behavior and curves up. So instead of having straight lines like this, the gas actually deviates from the ideal gas behavior like this. So at lower temperatures and higher pressures, the gas actually shows real gas behavior rather than ideal gas behavior. So remember, again, always ideal gases meaning ideal conditions, meaning higher temperature, lower pressure. Okay. And the next famous hypothesis you have already studied in chemistry, that is Avogadro's hypothesis, or simply the magic number that is known as Avogadro's number, that is 6.022 into 10 to the power 23. So how did this particular number came into play? As you already know that the law, or simply Avogadro's hypothesis, simply explains that at constant temperature and pressure, that is, pressure is also constant, temperature is also constant. At this particular condition, if you're taking equal amount of volumes of gases, that is, if you're taking 1 liter of oxygen or 1 liter of nitrogen or 1 liter of hydrogen, like that, in 3 different containers having same amount of volume, that is 1 liter, 1 liter, 1 liter, or 5 liter, 5 liter, 5 liter, like that, same amount of volume at constant pressure and temperature, then the number of molecules inside this particular container will be same for all. That is, if this contains 50 molecules, here also it will be 50 moles, here also it will be 50 moles. That is what Avogadro's hypothesis actually means. At constant temperature and pressure, if you take equal amount of gases in equal containers, that is, equal volume of all the gases, then they will contain equal number of molecules, or simply equal number of moles will be present everywhere throughout the system. That is, here also, here also, here also. Even though the gases are different, even if I take CO2, NO2, H2O, whatever it is, the amount of gas present in that particular container, if it is same, then the number of molecules will also be same. That is what Avogadro's hypothesis actually means. So again, just to quickly refresh your memories, let me remind you that from Charles' law, we already know that V is directly proportional to T. And from Boyle's law, we know that P is directly proportional to 1 by V, or simply PV is equal to constant. Here V by T is equal to constant. So we can just simply say that from these laws, we can actually write PV is equal to nRT. That is, PV by T will be equal to a constant. PV by T is equal to, again, just refreshing your memory so that you remember the chemistry you have already studied. So you already know that PV by T from the ideal gas equations, that is Charles' law, Boyle's law, and Avogadro's law. If you club all these laws together, then you know that PV by T is equal to a constant, and that particular constant is nothing but R, which is known as universal gas constant, which is having a value of 8.314 Kelvin inverse mole inverse. So again, this particular equation, if you rearrange it, we can say that PV is equal to nRT. That is, for n number of moles, PV is equal to RT, or If n is 1, it is PV is equal to RT. If there are n number of moles, we can say that PV is equal to nRT. So this is the ideal gas equation you are already familiar with. So it came from these three gas laws, which you should not actually forget. From Charles' law, Boyle's law, and if you apply the conditions, you can actually make the ideal gas equation. The only thing is that ideal gas equation is only obeyed by gases specifically at higher temperature and lower pressure. So if you want to imagine, you can imagine it like this. Your siblings who are studying in lower primary schools will be very sweet, very cute. They will do exactly what they are told. If they are told don't go out into the road, they won't do it. It's like ideal behavior. But if I say the same thing to you, you won't listen, you will do whatever you want. So that particular deviation from the ideal behavior is because you're not at LP, which is having higher temperature, lower pressure, higher temperature. But you're in more higher pressure. You'll be having more pressure and less temperature. So that is the deviation between real gas and ideal gas. So ideal gas will obey ideal gas equations at higher temperature and lower pressure. So this particular ideal gas equation can be slightly modified just by using Avogadro's hypothesis. So how can you use Avogadro's hypothesis to slightly modify this particular equation so that we can apply it in physics? So we already know that PV is equal to nRT, where P is pressure, V is volume, T is temperature, R is universal gas constant, and N is the number of moles. So number of moles, N, can actually be written as N divided by Na, where Na is Avogadro's number. Avogadro's number, that is 6.022 into 10 to the power 23. And capital N is nothing but number of molecules, and N is nothing but number of molecules. Remember, in your NCERT textbook, instead of N, it will be given as mu. Both are representing the same meaning. Since in your chemistry books, it is referred as N, that is why simply I took it as N. You can take it as mu also, it's completely fine. You just have to specify what it actually is. You can either take it as N or you can take it as mu. It totally depends. Again, you just have to specify what each thing is. That is, N is number of molecules, N is number of moles, and Na is Avogadro's number. Just like that, you have to specify what exactly each term is. Then it is completely fine. So again, we can write N as N by Na. So if I substitute that particular equation, then I can write this ideal gas equation as N by Na into RT, or simply nRT divided by Na is equal to PV. Right? PV is equal to nRT divided by Na. Now, if I take the ratio of these quantities, that is, instead of N by Na, which is equal to N, I am taking R by Na, that is universal gas constant R divided by Na as one singular quantity, and I am calling it as N by Na as a new constant Kb, and this particular constant is known as Boltzmann's constant. So this is known as Boltzmann's constant. Why this constant exists and what is the use of this constant will be studied at higher level physics classes, but not exactly right now in PUC physics. So remember that this is where the Boltzmann equation, or simply the Boltzmann constant, came from. You can actually physically calculate this particular value right here itself. That is, we already know what is the value of R and we already know what is the value of Na. So R is nothing but 8.314 and Na is nothing but 6.022 into 10 to the power 23, which means that if I take the ratio of R by Na, then I will get the number as 1.38 into 10 to the power minus 23, which is known as Boltzmann's constant, which is indicated by the letter K subscript B. So in thermodynamics and in kinetic theory of gases, we use Boltzmann constant, that is K subscript B, as the standard constant unit, and N will be the number of molecules that is present. So we can write this particular ideal gas equation as PV is equal to KB into NT, where KB is the new constant we just discovered, that is known as Boltzmann's constant. So PV is equal to KB into N times T, or NKBT. One more particular law is remaining, that is known as Gay-Lussac's law, and that particular law explains a relation between pressure and temperature when we kept volume constant. So when we kept volume constant and we took a graph between pressure and temperature, it was seen that pressure is actually directly proportional to temperature at constant volume. That is, pressure was directly proportional to temperature at constant volume. So when volume was constant, pressure was directly proportional to temperature, which means again the nature of the graph will be a straight line with a positive slope. So this again you already have studied this from the chemistry chapter. So again this will be just a general refresh on all the gas laws. So Gay-Lussac's law states that at constant volume, the pressure of a gas, pressure of a given mass of gas or given amount of gas will be directly proportional to its temperature. So this is known as Gay-Lussac's law. So the next topic is Dalton's law of partial pressure. So what exactly is Dalton's law of partial pressure? So Dalton stated that at constant pressure, that is, I'm keeping the pressure constant for a system. That is, I have a system here which is filled with a mixture of gases. Let's say there is O2 here, there is N2 here, there is H2 here, like that various amount of gases are there. The pressure of that entire system is fixed. Then Dalton stated that the net pressure of that particular system will be the sum of pressure exerted by the individual gases. That is, oxygen will be exerting a certain amount of pressure. Nitrogen will be exerting a certain amount of pressure, and hydrogen will also be exerting a certain amount of pressure inside that particular mixture. So these individual pressures, when we sum it up, we'll get the entire pressure of the system. That exactly is what Dalton stated. That is, at constant pressure, the total pressure of a mixture of gases, ideal gases, that is high temperature, low pressure. So this ideal gases is the sum of partial pressure exerted by the individual gases. That is, P net, the net pressure will be equal to pressure exerted by the first gas plus pressure exerted by the second gas plus pressure exerted by the third gas in this particular system. If there are n number of gases, then there will be n number of individual pressures to be summed up. So that is known as Dalton's law of partial pressure. Again, you don't have to take my word for it. We can just simply prove this using a simple mathematical trick. So again, we can prove Dalton's law of partial pressure is that. So let's say we assume that we have a mixture of two ideal gases that do not mix with each other. Let's take xenon and helium. So two ideal gases we are putting it in a container which is having a volume of V at temperature T and having a constant pressure of P. Then we can actually say that, okay, PV is equal to nRT. Right, from the ideal gas equation, we can say that PV is equal to nRT because everything is ideal conditions. But just one problem here, it is not N here, but rather it is N plus N. That is N1 plus N2. Now, what is N1 and N2? That is two gases are there, right? Helium and xenon. So, it means that N1 number of moles will be present for helium gas, N2 number of moles will be present for xenon gas. So, the two different gases will be indicated by N1 and N2 having N1 number of moles and N2 number of moles. So, we can actually state it as PV is equal to N1 plus N2 RT. All the other remaining quantities we have specified, and it is pressure P, volume V, temperature T, and R is again a universal gas constant. So simply we can write it as PV is equal to N1 RT plus N2 RT. And again, you can just take the V downstairs. So P is equal to N1 RT divided by V plus N2 RT divided by V. Now again, what is N1 RT divided by V? That is, we know that PV is equal to nRT. So P is equal to nRT divided by V. Right, using this particular relation, if this is N1, then it will be P1. That is, gas 1 will contain N1 number of moles and it will be exerting a P1 amount of pressure. Just like that, we can write this as first gas will be exerting N1, that is P1 amount of pressure. And here it is N2, which means it will be exerting P2 amount of pressure. So we have net pressure P net is equal to P1 plus P2. That is how you get Dalton's law of partial pressure. That is indirectly saying the net pressure of a system is equal to the pressure exerted by the individual gases at ideal conditions. And this is known as Dalton's law of partial pressure. This was a short introductory class just so you can refresh all the things you have learned in your high school and in your chemistry syllabus. So I'm going to be back with some interesting concepts you have yet to see in the kinetic theory of gases. I hope you have understood everything here. Until next time, thank you.